All right, so we're going to take a look at 4.4 optimization further today, but I wanted to just review 4.3, an extension of 4.2. 4.3 introduces what's called the first derivative test. And in 4.2, we've been noticing that using sign analysis on the derivative, we're able to identify regions of the, or intervals of the domain that yield a positive value for the slope of the tangent, which is the derivative, and regions that have a zero value and regions that have a negative value. And so this little diagram right here is basically the review of 4.2 and 4.3. So if you had a graph something like this, okay, what you want to notice first is that the point where the derivative equals 0, that is where the tangent line has a slope of 0, or where the derivative does not exist, which on this particular graph, it looks like it exists everywhere, okay? So, not including the beginning and ending points there, but everywhere on this graph, it's a continuous graph, the derivative exists everywhere. So we have several critical points where the slope, or the derivative value, is 0. So we're going to put those just underneath this graph in order to explain this. So there's a critical number. Here also is a critical number, right? Because the slope is 0 here. So we're going to put a 0 right underneath that C. Now, we have a slope of 0 here, actually. Okay, so at this point exactly, that's a slope of 0. So that's another critical number. Up here, that's another critical number. And right here as well. So you can kind of see in this diagram, I've got several different looking parts of the graph. And at each point here where there's a critical number, the derivative is 0. Everyone okay with that so far? Okay. Critical numbers, find the derivative, set equal to 0. Solve for the values of x, and those are your critical numbers. Now, what I want to kind of go over here is the first derivative test is testing the values of the derivatives to determine whether at a specific critical point you have a local max, a local min, or neither. Okay? I'll try and say that again. The first derivative test is examining the values of the derivative, whether they're positive or negative or 0, examining those values and how they change to determine whether a critical number is a local max, a local min, or neither. And so this is the beginning of this sort of thing. So we have 0 here. Now, what are the values of the slopes ahead of this critical number? So these are some tangent lines. Would you say that those slopes are positive or negative? Positive, yes. Okay, so in this region we have positive slopes over the entire interval before C and after our starting point. Okay, positive everywhere. At C is 0. That's important. After C, okay, you can kind of see that these derivatives, right, the values of the slopes here, are now negative. See that? All the way up until this next critical number. So you would put negative, negative, there. Okay. If we continue this on, okay, so here, a little bit faster now, this is positive, 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 right, all in this area. We've got 0, and then what are the slopes here? They are, they're positive again, yes, look at that. And so we have this happening. Okay, so that's going to be important. If you see this in your sign analysis, that's going to mean something. And then after this critical number, we have negative values for the derivative. And afterwards here, again, negative. Okay, so just take a few seconds to ingest this, okay, and tell me whether you agree with what I've done or not. Okay, does everything look right so far? Look correct? Okay. So what I'm getting at here is in 4.3, the only thing that's different is that we're actually calling this process of identifying local max and mins as the first derivative test. First derivative, we're going to test the signs and how they change. So I'm going to leave this graph up here. I'm going to get rid of some of the hair. I'm going to get rid of some of this ugly stuff here. Not that hair is ugly, but it's just distracting us. Okay. All right, so there's our graph. Now, the first derivative test says that surrounding a critical number, if you have the derivative changing from positive to negative, you have a local max. And that's exactly what we see at this critical number, a local maximum. So when the derivative changes from positive to negative, you have a local max. It also says that when your derivative changes from negative through 0 to positive, you have a local min, a minimum. And that's what we see here on the graph. Okay? So that's negative, 0, positive. The first derivative test would tell us also that if you have a positive interval, and then you have a 0, which is your critical number, but the derivatives immediately after that critical number on this interval are also positive, the same sign, then you have neither. So you do not have a maximum or a minimum. The sign has to change in order for there to be a max or min. And of course, when we look up at the graph in this area right here, it's pretty easy to see that this is not a maximum point. Well, it's a little bit, the y values would be a little bit bigger than these values, but they're a little bit smaller than these ones. So immediately around there, this is not a maximum at all. Okay? And that's how it translates using the first derivative test. All right? So again, moving quickly through here, if you have positive to negative, you have a max. And if you have negative to negative, you have neither. All right? And in summary, that's 4.3 right there. That's really all we're looking at. So you do your take a derivative, find the factors of that derivative, factor it down, and then you do sign analysis, and then you find out where the sign changes and where it doesn't, where your critical numbers are, and all that sort of stuff. Okay. Any questions? Okay, so there is the assignment for 4.3 on page 182. And that we worked on the week before the break when the Guatemalans were just gone. So you may have to get caught up on this. Okay, so 4.4 is applied max and min problems, aka optimization problems. So this is something that you're going to hear and see a lot of, okay? Especially if and when you continue on in calculus in university. Optimization, is a big part of differential calculus. Okay, that's a big part because this is an application, and when you can apply math, it's obviously important to a lot of different areas other than just pure math. So we also talked about, what sort of applied problems would we be talking about? Well, if we're talking about maximums, if you have some kind of function of revenue, let's say, in terms of number of people or in terms of product or in terms of whatever, but your function that you're describing mathematically is revenue, it would be of interest to you to find out what values of the independent variable would yield you a maximum revenue, right? So it's of interest to every small business owner or CEO or whatever to maximize revenue. Another thing we might want to do is maximize area. Okay, given the amount of material that we have to work with, what's the biggest area that we can create of, And one of the questions that we did last week was, you have a certain amount of material, you want to maximize the area of a pen that you're going to store, animals in a farm or something. So you have a certain amount of material, and you want to know what the largest pen is that you can make with that material. That is a very doable question in this arena. So minimum, what about minimums? Well, you want to minimize cost if you're running a business. You want to minimize, let's say, a sum. Okay, so you're looking for two numbers, and you might want to find the two numbers that yield you the smallest sum, and this is a problem you can use optimization in this calculus for. And of course, if you're given an area or a volume of something, and you want to minimize the amount of material that you're using to save cost or save money, or to be more efficient in some area, you might want to do calculus on the function of the amount of material that you're using. Okay? So those are some of the reasons why we're looking at this. Okay. Now, again, I handed out this worksheet, and we did some examples. And instead of going through this example right away, I think I'm going to jet down to the steps. Okay. Now, I believe that these steps were on the previous video. Okay. So you should have these steps on the video. I will go over them real quickly because we are kind of starting over again with you missions team people, but not really. So this is going to go quick. Okay. But here are the steps, and on page 185 is sort of, these steps are all explained in greater detail. So the first thing you want to do is understand the problem. So you want to know, what are you asked to find? Whether it's dimensions of a rectangle, okay, whether it's the amount of units that you're going to make to maximize revenue, given certain restraints. So you want to find out what it is that you're asked to find. Identify that, write it down. You can put, you can just write dimensions, and then equals question mark, or whatever it is that helps you remember what you're actually looking for. Because at the end of this question, it's going to be a long question, and you'll be like, okay, what am I trying to find again? I've got X here, and X represents something, and what is the question asking me for? So you got to make sure you wrap it up. Number 2, if you can, draw a diagram. All right, draw a diagram. Very, very helpful. And as you'll see as we do questions, there are some questions that you can draw a diagram for, and some that are a little bit harder. If you're looking for two numbers whose squares have a maximum sum, and their product is 75, well, that's not an easy diagram. I mean, how are you going to diagram two numbers, right? But if you're looking for a maximum area of a rectangle, then draw the rectangle. Label the parts with some unknown quantities, some variables, whatever, which is our step 3. After you've drawn the diagram, introduce notation. Okay? So you want to assign a variable or two, and I'll get into that a little bit more later, but one or two variables to the unknown quantities. So you want to introduce notation. So your length is L, your width is W. So you can use those variables. Step 4 is write an expression using one variable only. Okay? Now the reason is that we're going to be able to, take the derivative of our function that we are trying to maximize. And it's important that it's a function, not absolutely necessary, but it's going to be a lot easier if you can write it in one variable. So at this point, we don't want to do any implicit differentiation. We don't have to. Okay? If you write it as a function, it's going to be way easier. So in terms of one variable to represent the quantity that is to be optimized. Okay? So this is important, to be optimized. If you're optimizing area, then you want an area function. If you're optimizing sum, and you find a minimum sum of something, maybe you want to write a function that represents the sum. So this is important. The expression represents what it is that you want to be optimized. And then number 5, use calculus methods to find your max and min values. And of course, those calculus methods include finding the derivative of the function that you're trying to optimize, setting that derivative, and might be easier if it's factored, right? Setting that derivative to 0. Determine critical numbers, and then find out if they represent maximums or minimums. So that's the use the calculus methods part. Once the variable is solved for, you use that value to determine any other values in the question. And I know I'm going through this fast, I just need to have you write this down. We can come back to it, it's in the other video, whatever. But I'm just going to kind of keep going here. But once you're done, whatever you've solved for a value, okay, and you've determined whether it's a max or a min, and it gives you what you're looking for in the question, then you can use that value to determine other values that the question might be asking for. So in a nutshell, that's sort of the whole, that's what you do for all optimization problems right there. That is it. And I want to go over some more examples. And like I say, if you weren't on the missions trip, you've had a few days here to explore this already, to begin exploring this already. But I am going to go over some examples for those of you that haven't seen these yet. Okay, so we're going to take a look at example 1 on page 183. 4.4 in the text. And it says, find two positive numbers whose product is 10,000 and whose sum is a minimum. All right. So if we look back to our steps, okay, this is not an easy one to draw a diagram for because it's asking for two numbers. So you don't typically draw a diagram for this one. But what else does it say? Oh, understand the problem, of course. What do we ask for? We're asking to find two positive numbers. So you're looking for two positive numbers. Okay? That's what you're trying to find. So just remember that. Write it down, whatever. And you're also given that their sum is what you want to maximize. And actually, you want to minimize the sum. So the sum is the function that you're going to want to create here. That's what we're going to do the calculus on. All right? So I'm just going to hold off on that. Don't write anything down on there yet. Assign values. Okay, so the two numbers could be x and y, let's say. And it's okay to use two values for now. X and y. So one of the numbers is x, one of the numbers is y. Now, there'll always be a little bit of information that you can write an equation connecting the two numbers. Okay? So in this case, they say that they're looking for two numbers whose product is 10,000. So you know, because the question tells you, that the two numbers multiply to 10,000. So you're going to want to just write that out and keep that in mind. Why is that? Because that's going to help you write this equation in terms of one variable only. All right? So just leave that there for now. And then you go back over here and you say, okay, what do I want to optimize? The sum. And that is the sum of both of these numbers that I have identified, right? Two numbers, unknown numbers. Now in your steps it says write the equation to be optimized in terms of one variable only. Well, now we have two different variables, so that's no good. So what you want to do maybe is say, okay, I've given this information. Let me solve for one of those variables. And in order to do that, you can just divide both sides, in this case, by x to solve for y. And now you have y in terms of x. So you have y all by itself. Notice that y is one of your variables here. So because of this statement of equality, you can actually put 10,000 divided by x in place of y, and then you've eliminated the second variable. So I'll say that again. You can replace y with 10,000 divided by x because that's actually what y equals given the other information in the problem. So now we have x plus 10,000 divided by x. So do you see how this now, we only have one variable there? Okay? That's huge. You will be able to do that with all of these ones. Okay? And you want to try and do that. You want to try and manipulate things so that you have one variable only. And now this is a function of x. So it's a sum in terms of x only. We okay so far? Everybody with me? All right. So at this point, now what we want to do is we want to go back to our steps here real quick, and it says what? Use calculus methods to find the max or min. Okay. How do we do that? Derivative. Set that derivative to 0. Determine critical numbers. Find out if they're maxes or mins. All right. So we shall do that. Let's take the derivative. The derivative of this. Now x is our preferred variable, right? We're actually doing ds over dx, right? So x is the derivative, the preferential variable. So the derivative of x is 1, right? Remember that. And so if we do this, this is quotient rule. Derivative of the top is 0 times the bottom minus the top times the derivative of the bottom, which is 1. So that's minus, I'm skipping a couple steps here because you should know how to do this. It's minus 10,000 times 1 all over the bottom squared. So this is what you end up with when you take the derivative of that second term. If you have to do that in steps, go ahead. Right? but that's your derivative. Okay, everyone with me there so far? Yeah? Okay. So at this point you have, I guess, some options. You let this equal 0, so you can just throw a 0 down there and say, hey, what is my x value when this happens? Right? And, okay, well, you can isolate for x there. It's only in one spot, so that's no problem. So you got 10,000 over x squared equals 1, right? Because you move all this negative stuff over to the other side. And x squared then is 10,000. And so x is the square root of 10,000, which is what? 100. Now, sorry? Okay, yeah, that's just what I was going to say. Technically, the square root of 10,000, if you're taking a look at just straight math, it's plus or minus 100. Now, I only wrote down 100. Anybody know why I just wrote down positive 100? Because the question says, exactly, the question says I'm looking for two positive numbers. So negative 100, I can reject it right away. Okay, it's an answer that algebraically I would arrive at. But according to the problem, I already know that I'm looking for positive numbers. So x is one of the positive numbers, it looks like. See that? X is one of the positive. So one of them is 100. Now, those of you that have been working on this for the last few days, really, a few classes, you know that if you're maximizing an area, a lot of times the shape is the dimensions are pretty close to one another, aren't they? Okay, so we're seeing this as a pattern a bit. And here, of course, x times y is 10,000. And so if x is 100, we're looking for y, of course, that's y is 100 as well. So the two numbers look to be 100 and 100. Well, let's go back to the question, and first of all, let's reason together. Now how do we know that this x value, I guess my question is, how do you know that this is going to yield you a minimum sum or a maximum sum? Like how do you know what this, because this is a critical number, right? So how do you know if this is not a critical number here, yielding a maximum, or a critical number here, yielding a minimum? How could we find that out, or what do you think about that? Like, is 100 and 100 my answers, or would there be something different? Okay, two different things you can do. You can think through logically and say, okay, 10,000 times 1 is a product. Those are two positive numbers. What's that sum? That sum is 10,001. 5,000 times 2, what's that sum? Well, that's 5,002. 100 times 100, what's that sum? 200. So we're talking about like 10,000, 5,000, and 200. So does it make sense that there might be a minimum, or does it make sense that there might be a maximum, or what? Obviously, this 100 yields a pretty small sum compared to the other options that we have, right? So if you think through it logically, you think, yep, this critical number is going to yield me a minimum, because I'm just running through some other possibilities in my head, and all the ones that I'm thinking of are greater, a sum that is greater than what this one's yielding. Okay, that's method number one. Think through it logically. Of course, method number two sometimes is what we've been doing, and that is, doing a sign analysis. And you can do a sign analysis using test points. You don't have to factor this whole thing. You don't have to. I mean, you can, but you don't have to factor it. You can do a quick sign analysis using test points. And so if we know that this is our derivative, right, this is what you could do. You could say, all right, here is 1 minus 10,000 over x squared. That's my one factor, let's say. And I know that I have a 0 at 100. Right? Okay. So if I put in a value of 100, that's 1 minus 10,000 over 10,000. That gives me 0. That is true. You could use test points to find out if this is positive or negative ahead of that. And this is the crux of what we've been doing last section. So a test point, let's say this is 0. What happens if we put 0? Oh, that's a bad one, isn't it? 0 is a bad one, right? 10,000 over 0, no good. Okay, so let's pick something else. What about 10? 10s over there. So what do you get when you have 1 minus 10,000 divided by 100? Do you get a positive or a negative value? Yeah. 1 minus 10,000 over 100, that's 1 minus 100. So that's going to be big time negative value there. Okay? So our derivative, and then this is your sign analysis, negative here, 0 there. And if we have a number that's greater than 100, obviously this is going to be 1 minus 10,000 over something larger than 10,000. So that's going to be just a small decimal. This is going to be positive here. Okay? And that's using test points. So what does this tell us? Negative, 0, positive. That's this one. Negative, 0, positive, local minimum. Okay? So if you're wondering at all, hey, is this going to yield me a max or min? Two choices. Think through logically, or use sign analysis with factors or with just the whole derivative using test points. All right. So the two numbers then are 100 and 100. That's what you would say at the end. And I need you to write a quick sentence, circle it, kind of to conclude everything. Okay. Do a check if you want to. I did a mental check there with the sums and stuff. That seemed to work out. I didn't check every possible, sum, but I did enough. So the two numbers are 100 and 100. Now, they're the same. Yes, I know. So does it seem a little silly to say the two numbers are 100 and 100? Well, I guess it's saying two positive numbers, and yes, they are the same number. That's okay. They don't have to be different. They can be the same. Okay. Now, does that align itself? Let's look at the text now. Does that align itself with what the text is saying? Yes, the two numbers are both 100. Okay. So again, I do examples in the text so that if we get off track, we can kind of go back and say, oh, hey, that's where we went wrong. But also we can confirm what we're doing. And obviously, there'll be slight variations between the way I do it and the textbook does it. So that may help you if you compare the two if you're struggling. Okay. No other questions? Okay. Let's do, now, one of you asked about the volume question on that assignment. So with the box that's cut out, I wonder, yeah, you end up getting it? Okay. 4 was more of an issue in that sheet. Yeah, 4 was a tough one. Yeah, all of them basically. 1, 2, 4, 6, 7, 5. Yeah. Okay, thanks. Well, the thing is with this worksheet, I do kind of want you to struggle through it a little bit and see what you can do on it. You're struggling all right? Okay, got that part under control? Okay, good. The struggling part is accomplished? Okay, great. All right. I tell you what, I'm going to go over some similar examples, okay, so that you can, hopefully that'll help out. I kind of did one that's similar to number 6 there. Oh. All right, let's do example 2. Okay, let's do example 2. Example 2 says we have 2,700 meters squared of material. And you're able to make a box that has a square base and an open top. Oh, here we go. Let's draw a diagram. Now your diagram skills may be, let's say, emerging. That's fine. You don't have to be perfect at it. But it should somehow resemble some kind of box. Now it says it has a square base. So that means that the length and the width down here at the bottom should be the same. Right? There's your 3 dimensions now. And your height is going to be here. Now, you could do B and B or other variable, it's the same, whatever. I'm going to keep height as height because that makes sense to me. That's the height of the box. If I did X, X, and Y, that would be okay too because X is horizontal, Y is vertical in the math we do. But if you did, K, K, and W, what's Y, right? So at least h I know is the height. That I'm going to be able to watch that as I go through the question. Okay. It says, we want to. What do we want to optimize here? What does it say? We want to optimize what? Yeah, okay, we want to find a maximum, okay, and what we want to maximize, or just generally optimize, is the volume, okay? You see what it says that? It says find the largest possible volume of the box, okay? Okay, so I'm not going to write anything in here right now, right? But we know a few things here already, and you just got to work at connecting the dots here, okay? So notice I've written down some things here. I am looking for the largest volume, so that's what I'm asked for. And I know that I have a box, and I know how the volume and the dimensions of the box are related. I know how that's related. And so there you go. You think of some kind of equation that you can connect some things with. And the added information that the volume is 2,700 meters. So watch what I'm doing here. So volume of the box is going to be what? Length times width times height. So that's actually x squared h. Or hx squared, doesn't matter. I'm given that the volume is 2,700 meters. Wow. Okay, that's good. So the volume is 2,700 meters. So that formula, actually in this particular question, x squared h is 2,700. Okay. Oh, the material is 2,700. Oh, that's true. Okay. So I am on the wrong track here. Thank you for that. Thank you for that. That is the volume, but you're right. This is material. Thank you. I got a little mixed up there. So this is not the one we want to use. That's still a volume, and actually that is going to go here. I should have put that here, actually. This is the volume. That's what we're trying to maximize. And the 2,700 is the material. Thank you for that. Okay. So how do I write an equation connecting this 2,700 and these variables? Because we still have to do that. Okay, so the equation connecting 2,700 meters squared of material and the variables here in our diagram, in our question, look like this. Okay, we've got an open top, but we do have to account for surface area, right? That's really what this is. So we're going to have x squared, that's the area of the bottom, right? And then we're also going to have plus h times x plus h times x plus h times x plus h times x, 4 times. So 4 of the side flaps, 4 xh's. Okay, does that look right? That is better, yes. 2,700 is the material. So we can fill that in, 2,700. X squared plus 4xh. And now what we want to do is we want to say, okay, I've got the volume that I want to be maximized, but I've got 2 variables. I want to get that down to 1. So I need to express either x or h in terms of the other variable, so I can have 1 variable only. And that's when you look at this other information that you're given, and you say, hey, I actually can pretty easily solve for h here. So let's do that. So we have 2,700 minus x squared. Okay, gets rid of that. And so that's going to equal 4xh. So I divide by 4x. Everyone see that? So I've taken this equation here, transformed it into this equation, isolating for h. And now this h right here, which we see over here in the volume, I can substitute for what that h equals, and that is just in terms of x alone. So that goes right there. Okay, so you guys will have your steps handy if you want to keep looking through your steps. Same sort of thing. I don't want to scroll back. You with me so far? Doing good? Okay. So now I can rewrite this volume in terms of x now. This is volume, a volume function in terms of x. Because what I have is x squared times 2700 minus x squared all over 4x. And you may want to simplify this before you start taking the derivative. So we've accomplished something in that we have, in terms of one variable only, this is the formula for volume for that box, and we've included the information given about the amount of material we have. All right, so what's another way we could write this? Well, that squared goes with that x, right? And we could multiply this x in, so we just get one term. Well, that might be a good idea. So 2700x minus x cubed over 4. We could do that. Now in the textbook they divide this into two terms, but you don't have to. I think it's just as easy. We can do quotient rule just as easy as the other, but you can do whatever you want. So like they do in the textbook, they do 2700 divided by 4 to get 675x, and then minus 1/4 x cubed. So they do it in two separate terms, which is totally fine. This is quotient rule, right? Quotient rule, but you get the same answer as if you do just product and sum here. Sum difference rule. Okay, so whatever's easiest. I would probably tend towards this, but you don't have to do that extra step if you don't want to. Okay, so now that we've got this one in this format, let's just take the derivative of this. So b prime of x is 675 minus 3/4 x squared. Okay. And if we find the critical number now, so we let this derivative equal 0, we have 3/4 x squared equals 675. X squared equals, and you can do your 675 times 4 divided by 3, 900. Yeah, it's 3/4 over here. But when you take this over there, it's times 4 over 3. Because 4 over 3 gets rid of it over here. Right? So then 900, so we have x equals, what's the square root of 900? Should be 30, right? Now, plus or minus 30, yeah. But, to go back to the question, we're not talking about negative distances. That doesn't make sense, right, as far as a length. So we're only looking for the positive. And in a lot of these word problems, you'll just be rejecting the negative values for your critical numbers. So yeah, so 30. And that's for a value of x, so that looks like that's the dimension for the base. Okay? Again, there's only really one critical number in the domain. There's only one. So you'll see that most of the time when we're talking about optimize the volume, and they actually give it to you in the question, what's the largest possible volume, you know that this critical number is going to yield you a maximum. But again, you could double check always. Take this derivative, right, and do your sign analysis if you want. Blah, 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 blah. Where is this 0? Here's 30. Test this value, test this value. Make sure that you get, positive here, 0, negative there, a local maximum. You can always double check that way. But 30 is going to give you the largest possible value. So we want to find the largest possible value for the box. So this box actually looks like this. It's 30 by 30 by, we don't know. How do we find that out? Well, we go back here and say, well, how can we figure out the other stuff? Oh, check this out. I have this equation right here, the equation for the surface area, that transformed into this. Look at this. You can just plug your x's in there and get your h value. Right? So write that down there. So our h is going to equal, if I plug 30 in for each of these x's. Okay? So this is 2700 minus 900 all over 120 equals h. So what's that? 1800. Sorry? Thank you. 15. All right. So the largest possible volume is 30 squared times 15. 1350. 13,500. And if you stop there and said that's the largest possible volume, I said it again, volume. Largest possible volume, okay, we would be slightly deficient, right? This is not a good answer. Volume equals 13,500. Well, what are we missing? We're missing units. So we didn't write that, we did write that down. Did I write this down? Oh, it was a little hasty. That's centimeters squared. So we are dealing with centimeters. And this is a volume, so it's centimeters cubed. Okay? So, again, the maximum volume is 13,500 centimeters cubed. So that would be a better answer than just writing your number. So if it's a word problem, write a word answer. That's a good rule. Okay, questions? So the 4.4 assignment is I would like you to do number 1 and 2. Those are really easy ones. And 5. Those are the 3 questions that, I've basically done the exact same questions for you. Number 8 as well. Good one for you to do. Number 10 is a bit outside the box a little bit. And yeah, let's do number 16 as well. So those questions here, you should get as many of those done for tonight as possible. I'm thinking kind of the first 3 or 4. You can take a little bit of time next class to finish that. And then I'll be giving you your optimization handout assignment that will be due Friday. Okay? So you can work until the end of the bell. End of the class.